Okay, so we talk about one algorithm to find the shortest path, especially the single source shortest path. Single source shortest path. So single source means we have given the source, that means one vertex is a input also. So what is the input of this algorithm? Input is basically a graph, directed graph V comma E, directed graph V comma E, and a weight function E to R and a source vertex. And so a given vertex is also a input, that is the called source vertex, and the problem is to find the shortest path from that source to all other vertices. So output will be, so the weight of the shortest path, so delta of S comma V for all V. So this is basically delta is denoted delta of S comma, so basically delta of as we know from the last class, delta of U comma V is, we defined the weight of the shortest path, weight of the shortest path from U to V. So U V are any two vertices, then weight of the shortest path from U to V. So first of all, for that, so if there is no shortest path from U to V, we define this delta of U V is infinity if no shortest path from U to V. Okay, and in the last class we have seen if there is, so what are the condition? There will be no path from, no shortest path from U to V if there is no physical path from U to V. So that is one option, and another option is, although there is a physical path, if there is a negative cycle. So if there is a negative cycle between the path from U to V, then there will be no shortest path. So U to V, if there is a path, but there is a vertex Vk such that there is a negative cycle in the path. If there is a negative cycle, then there is no shortest path, because if we can loop in this cycle. If we claim this is my shortest path, I will make another loop. So that's why if negative cycle, then there is no shortest path exists. So to have the shortest path, so we have to have the physical path and no negative cycle. So this algorithm, for this algorithm cannot handle the negative cycle. So that's why this algorithm we assume this weight to be non-negative weight. So we assume this weight function to be non-negative. So for UV are basically non-negative weight for all UV belongs to E. So this is one of the assumption for Dijkstra's algorithm. For Dijkstra's algorithm, because Dijkstra's algorithm cannot handle the negative weight cycle. So that's why, to be safe side, we take to this weight to be every weight is positive. If the weight is non-negative, then there is no question of having the negative cycle in a path. Okay. So this is the input and the output is deltas. Now this is a greedy approach. So this is basically a greedy approach, and the idea is, so idea for Dijkstra's algorithm is greedy basically. So what we do? So we maintain a priority queue, we maintain a set S of the vertices whose shortest path distance from from small s is known. Okay. So basically we have a graph G and we have all the vertices. Among these vertices we choose, this is one of the vertices as the input, S, and the capital S basically set of all vertices for which, we know the shortest path from S to that vertex. Now obviously small s will be in capital S. Why? Because, so what is the delta of S comma S? Any guess what will be the delta of S comma S? It is 0. Why? Because we are not having any negative cycle. There is no negative weight H, so there is no negative cycle. So if there is no negative cycle, so we are at vertex S. Now what is the best way, what is the shortest path from S to S? So there is no negative cycle. So if though there is a cycle, that cycle will be positive cycle. So better to remain as S. So delta of S comma S is 0. So there is no other way we can reduce the weight less than 0, because there is no negative cycle. So that means delta of S comma S 0. So S will be the first vertex which will be in capital S. Okay, because delta of S comma S 0, and then we will slowly capture all the vertices in S. Okay. So that is the in a greedy way. So let us just but S is the vertex, S is the set of vertices for which if V is in S, then delta of S comma V is known. Once we know the delta of S comma V, then we capture this V in S. So we maintain a set S of all vertices whose shortest path distance from S is known. Okay. So that is the our capital S set. Then how to grow this capital S? This is basically by the second step. At each step, so we have distance estimate from S to, so at each step add a vertex to S, add to S a vertex from V minus S, whose distance estimate estimates from S is minimal. This is the greedy choice. So what we do? So we have the set S. Now this is the V minus S, all other vertices. So small s in is S. Now every time we are adding a vertex from, so these are the vertices which is having some distance estimate. So this distance, so this is a V is one of the vertex. So it was having some distance estimate. Now we consider all the vertices over here whose this dV we denote by the distance estimate. We will come to the algorithm, the pseudocode. dV is denoting the distance estimate from S to this node V. So we choose one of the vertex whose distance estimate is minimum, and that is the greedy choice, and that vertex we take it into the S from the Q. Okay. So basically we are maintaining a priority queue from the with the all other vertices other than S, and then we are extracting the minimum from this queue. Okay. So this is the idea. So we choose, then once we capture this V in S, suppose this V is distance estimate in S. So we capture this this V in S, and then we have all the vertices which are connected to V. So this is our say new U. So we have all the vertices which are connected to this V. So this was having a distance estimate D of V1 say. Now we have, now this is capturing S. So, once it is captured in S, so that means for that vertex delta of S comma V du basically this. Once we capture a vertex in S, for that vertex the degree will be the delta of S comma U. Now, this vertex which is directly connected with this vertex which we have just added in S. Now, this vertex was having one distance estimate. Now, we have a distance, we have a path from this to this with this du, and then we have this direct edge. So, this is basically what is the weight of this new path to S to V1. So, S to V1 is basically du plus W of U comma V1. I mean U is this V. Now, if this is better than the path we have, if this is less than the distance estimate of V1 we have, then we have to update this, then we got a better path. So, this means we are having a path from S to that vertex V1 with a cost d of V1. Now, we have a new path. Once we capture this in S, capital S, then we have a new path. We can go to S to V, then V to this, and that then this path weight is this dV or du plus this, and if that is having less weight than the earlier path we have, then we must update that, we must take the new path. So, that is called relaxation. We are relaxing this edge. So, relaxation means if we are updating the degree of this by a new path, if it is better than the what we have already. So, that is called relaxation. So, we may have to relax this. So, at each step we will do this. So, let us write this. So, this is basically every time we are capturing a vertex in S, and then we update the distance estimate of the vertices which are adjacent to V. Distance estimate of the vertices adjacent to V. Okay. So, this is the idea of behind the Dijkstra's algorithm. So, now we will in a moment we will write the pseudocode for Dijkstra's algorithm, and then we will go for an example. Okay, so let us just write the pseudocode for Dijkstra's. So, the idea is greedy. So, every time we capture a vertex in S in a greedy way, because we are taking the minimum we are taking the vertex whose distance estimate is minimum. So, that is the greedy choice. Okay, so this is the algorithm. So, Dijkstra's algorithm. So, what are the input? Input is a directed graph, and we have a edge weight which is non-negative, and then we have a source vertex. So, this is a single source shortest path. So, given a vertex S, we need to find, this is any vertex could be the input, but this is the vertex, this is part of the input. Okay. So, we are defining degree of S to be 0. This is basically giving this degree is we are maintaining as a distance estimate from smallest to any other vertices. Okay, then for all other vertex V, which is this is the initialization phase, do dV equal to infinity. This is same as the Prim's algorithm. This is the initialization step, because initially nothing has explored. So, we are putting the degree to be infinity for all other vertices, because we haven't explored yet. So, that means, that is why we are putting infinity for all other vertices. Okay. So, this is 3, 4, and now we give S is initialized by infinity, and then we put a priority queue to all other vertices. So, this is the priority queue. Q is basically is a, like we did in Prim's algorithm, priority queue maintaining V minus S basically. Okay. And every time, and this priority queue is this keyed as the degree of that vertex, and every time we extract a minimum from this queue until the queue is empty. So, this is the operation while queue is not null, we do extract minimum from this queue. So, extracting minimum means we are deleting from the queue and we are adding in S. This U is added in S. Okay. So, we just capture. So, we just capture a vertex in. So, initially S is in this set. Okay. So, then we capture a vertex which is having the V, which is so this is U, which is having the minimum degree. So, we capture this in S. Then what we have to do? We have to update the distance estimate of all other vertices which are adjacent to V. So, that is basically we need to do now. Okay. So, this is 7, this is 8, so 9 is. So, now we need to this is 8. So, for all vertex, so after extracting for all vertex V which are in adjacency vertex of U sorry. So, what we do if, so suppose this is our U, now this is our V, one of the V. So, it was having a distance estimate dV, now this is our S somewhere here. So, we have, so this is the, now if the degree of V, so distance estimate of V which is having is greater than du plus W of uv. So, what we do? We go from S to U with this path, and that is the shortest path, because once we capture a vertex in S, capital X, that degree will become the shortest path of S to that node, and then we take the direct this H W of U comma V. So, this is a new path from S to V, and weight of this path is basically du plus this, and if this weight is less than weight of the path what we have, then we must update this weight, we must take this new path. So, that is then dV must be updated by this new path. Okay. So, this is 10 and this is 11. So, that is it. So, this is the pseudo code for Dijkstra's algorithm. So, this step is called, this step what we are doing is called the relaxation step. Relaxation step. So, basically if the already we have some estimate, distance estimate from a vertex V. V is the vertex which is adjacent to the vertex U, which is just recently captured in capital S. Okay. Now, already V is having some distance estimate. So, that means already there is a path from S to V with the weight dV and initialized by infinity, because initially nothing has explored. Okay. Now, we have a path. What is that path? We go from S to U with a cost du, then plus we take this direct H WUV, and weight of that path is du plus WUV. Now, if the weight of this path is better than the weight we already have, then we must relax this, then we must take the new path. Okay. So, that is called relaxation. We are relaxing the edge because we got a new path from S to this vertex V. So, that is the idea, and this we will do for all the adjacency vertices of U. Okay. Okay, so now and this is the relaxation, and this step is basically same as decrease key operation, which we did same thing and in the Prim's algorithm, decrease key operation, and then this step is called, this is the extract mean. So, depending on how we implement this in a data structure, it will take the time. So, before going to the example, what is the time complexity of this algorithm? So, time complexity is basically, this is this step is basically theta 1, and this step we are doing is basically theta of V times, and this is basically theta 1, and here this Q, this is a while loop, and this loop is running up to V times, because it will keep on running until we exhaust the vertex. Okay, so this step will be running order of V times, and inside that what we are doing, this we are doing the extract minimum. So, again depending on the priority queue, how we are implementing, that will, if we are using a array, just we are using the vertex we are putting into a array. So, the extract minimum means we have to choose the minimum. So, minimum will take the order of n time. So, depending on this, but if we use the mean heap, as we discussed in the Prim's algorithm analysis, if you use the mean heap, it will take the logarithm time. So, this is the time for this. So, time to extract minimum, time to extract minimum, and we have, this is what we are doing, time to extract, time to decrease the key. So, if we have to relax this vertex, then we have to go to that particular field and we have to change the degree. So, for that we need to, if it is array, we are going there, we are changing. So, that is constant time, but if it is a heap, if we change it, it may violate the heap property, mean heap property, again we need to heapify that. So, this is basically time to decrease key, how many times, this is the degree of this time. So, summation of time for decrease the key. So, if we just write the this time complexity of this, it is same as, we will see it is same as the Prim's algorithm times complexity. So, basically it is just write the time complexity of this. So, so this part is, so time for Dijkstra's algorithm is basically order of V times extract minimum plus, so this is outer loop is order of V times. Now, this is basically summation of degree times we are doing. Now, summation of degree is basically, this we have seen, this is the Hansaking lemma, order of E. Okay, so this is basically order of E times T of decrease key operation. Okay, so this is time complexity is same as the Prim's algorithm, and depending on the which data structure we are using. So, if we are using heap, then this will be if we are using an array, then this will be order of V, and this will be constant. So, whole will be order of V square, and if we are using a heap, then this will be order of log V. So, this will be again order of log V. So, depending on that, so this will be E log V. So, anyway, this is the same as Prim's algorithm. Okay, so now we will talk about, we will take an example for this Dijkstra's algorithm, how it is working. So, let us take an example of a graph, and on which we can have the Dijkstra's algorithm. Okay, so example of Dijkstra's. Okay, so we take a graph. So let us take this graph. So these are the weight 3, 2, 1, 4, 8, 2, 7, 9. Okay. So this is the given graph, and this is a directed graph. So this is a directed graph, and we are having the edge weight are non-negative. So there is no negative edge. So that means if there is a shortest path from, if there is a path from U S to, so S is also has to be another input. So if there is a shortest path from S to a vertex, then there will be a if there will be a path from S to a vertex, then there will be shortest path. Otherwise, that S will be infinity if there is no physical path from S to that vertices. Okay, so we will continue this in the next class. We are short of time now. So from next class we'll complete this example. We'll work out the Dijkstra's algorithm on this example. Thank you.